We're live. All right.
Okay.
Welcome again,
Right.
repeat viewers to I Can Science That. I have a new guest today, Peter Leane. And would you like to introduce yourself a little bit?
Yeah, hello. I'm sort of interested in the conspiracy and investigating the pendulum, I guess, flat Earth. That's enough, I think.
Okay.
You take it away and ask me the journey. If you want to go that way, or
Well, yeah. Let me
my background,
introduce.
my background, maybe. Yeah, that.
Yeah. Okay. Go ahead.
Yeah,
A little background.
yeah. Basically, started off in electronics, done a million things. Ended up as a handyman as I approached retirement. So I've crossed a lot of fields. If you look at my channel, I'm into a lot of things from researching the spinal cord. Something I used to get a lot of interest in was my perfect gun. It was a method to. A lot of people ask me about that. That's interesting. It was the most accurate gun in the world. And I get a lot of interest on that, but it wasn't actually a gun. It was to prove, spinning the barrel.
You were spinning the barrel as opposed to like just rifling the bullet.
Than rifling to create stability.
Uh-oh, we lost some bandwidth.
Channel.
I'm not sure whose that is. Maybe the viewers can tell us, is Peter coming through okay? Am I coming through okay? I'm getting a little choppy from Australia, but it could be me. I'm in the Pasadena area and we're on fire. Okay.
Yeah. Wow.
Okay. So yeah, Peter, you're lagging a little bit.
That's another subject.
Okay. So yeah, you talked about the spinning gun and how that improves the straightness of
it creates stability rather than rifling. That was another side issue. Was trying to get a projectile to go dead straight, a ball or a sphere. Quite easy with a conical bullet and rifling, but to get a round ball to travel straight is quite different. And that was to do with the jumping the synaptic cleft of a motor neuron.
Really?
Okay. Yeah. The synaptic cleft is, if we scale that up, where motor neurons, the neurotransmitter jumps the synaptic cleft, which is a gap between two neurons. How they talk to each other. They talk chemically. Neurons.
Mm-hmm.
So, anyway, that's get back to on track. Oh, you got to pull me up because I'll go off on a million tangents here. So
okay.
Get me back on.
I'll tell you the first thing I saw of yours. First of your videos that I saw, I got interested in, was the rocket in a vacuum that you did.
Okay, that started. Wow, that was a journey. Basically, I had a very close friend, and he had a bit of trauma in his life, and he lost his job. He bought a new house, a big mortgage. He lost a grandparent, and he had a road to Damascus experience. I don't know whether you're familiar with that road to Damascus experience.
Tell us more.
I'm basically a Christian and working on it. I'm not a perfect one, but he was an atheist, and Saint Paul was I guess he was a very highly educated Jewish scholar, and he was out to persecute Christians. And on his way to Damascus, the Creator, or Jesus, appeared to him, put him blind, sent him blind, slapped him around a bit, and virtually converted him to a Christian instantly. So he went from a dedicated, highly educated Jewish scholar who was out to persecute Christians to a instant Christian.
Oh, okay. Yeah, I wasn't even familiar with that story.
Yeah, and I've heard about this, people. It's called the Road to Damascus experience, where they see a bright light and God talks to them.
Okay.
Right. Now, he was an atheist. This friend of mine was an absolute atheist. I couldn't talk to him about anything about Christianity.
Right.
And
so your friend was an atheist, but he had an experience, and now he
went 0 to hero Christian in microseconds.
Okay.
Yeah. So that put that in the write that down too. That's a part of the journey.
Okay.
Because all of a sudden he changed. Now I've heard about this. People, I've heard this thing. It's really something to research. Probably most Christians come to Christianity slowly, through a slow process. Very few go through this so-called Road to Damascus experience, where you get zapped. Anyway, things like his knowledge of physics. He used to come to me for physics and maths. Within 6 months, I was going to him.
Wow. So he got really into physics at that point.
Oh, yeah. He just understood
He got into Christianity and into physics. Although I'm expecting you're going to tell me he got into biblical literalism.
No.
Okay.
Oddly enough, no. He stayed away from all that.
Okay.
Yeah. So he was a really, I guess, a perfect scientist. Just like he went a bit crazy there for a while. Now he was suffering. I would consider it depression, or something like that. And I was talking to him one day, and he come to me and said, "Well, the Earth's flat too." I said,
how does a scientist, somebody who's like really into physics and science, how does he come to this conclusion?
Look, hey. He ticked all the boxes. He ticked all the boxes for going the other way.
Okay.
Anyway,
all right.
I was only a week before I'm telling him about my involvement with NASA. I said I was on duty the day the Columbia space shuttle exploded in '86. I heard the last words of the astronauts. Blah blah blah. Don't give me, don't talk to me about. He said that was right. The moon landing's a fake. All that stuff,
Right.
Another box ticked.
Right.
So
I mean, of course, you can't believe the Earth is flat if the moon landings are real. That's right. That can't happen. Okay.
So then he says, "I've got to. I need this. He needs help. I've got to step in here, because he says. I said my biggest argument was, hang on, if the Earth's flat, how come we go and take a rocket up to space and look at the Earth from outer space and we see it's round, a globe?
Yeah.
We have been. I was in 1969. I watched the moon landings. I worked with NASA for a large chunk of my life. Don't talk to me about it. And he said, well, rockets can't work in a vacuum. So that's where we started, with rockets in a vacuum.
That's where you started.
Yeah. So I said, well, look, rockets work in vacuums. They're reaction. Newton's third law. Bang. Stop arguing. They don't need an atmosphere to work.
Right.
This is ridiculous. They can work in a vacuum. No, they can't. No, they can't. So that's where I made the demonstration. And the first lot were a bit clunky. And the always argument was it's coming off. This seems to be typical. Most people would say rockets are they're tracking off something. They're hitting the bottom. They're reacting off the bottom of the launch pad, or they're reacting off the sides, or there's some air left.
Right.
you know.
Right. The
Now, I was thinking,
contention. I mean, I think most people who are going to watch this, they probably already know that a lot of folks believe that a rocket works by pushing, that the exhaust from the rocket pushes against the air behind the rocket, like and like it's jumping off or something. Like when you jump off the floor, you have to push against the floor. And I think they make that same connection with the exhaust from a rocket has to push on what's behind the rocket, right? They think that. And
yeah,
so
exactly.
you built one with a vacuum, and the immediate response is, oh, well, the exhaust just extended down to the floor of your vacuum or to the walls of the vacuum. It's pushing on something, right? Um, yeah.
Yeah,
Hey, Blue
exactly.
Marble.
So
Sea
I
Lion's
got
here. Go ahead. Go ahead. So you built
yeah,
the thing, and he said no, and then you built a bigger one,
yeah. Then I
right?
made it 6 meters long. 6
Right.
meters long. I said, okay, and it's going to touch the bottom now, is it? Nope. Okay, you agree with that? And it's not going to touch the sides because if it does, it'll be like climbing up a well with your fingernails. Yeah, yeah. He said, okay, it won't touch the sides.
Okay.
So then I did the launch, and I had to slap him in the face about 3 times to bring him to reality. He just was so gobsmacked to see this thing actually flew. He was so gobsmacked that it actually worked. Because then his science kicked in, and everything I told him registered. There was a touching bottom. It wasn't reacting off the sides. And there's about 3 molecules of air in this thing. So what's it reacting off? So he said, yeah, okay. Rockets work in a vacuum. So now NASA you can understand that NASA can launch a rocket with a camera on it and send it into space. And they can take a photo of the Earth. And he said, yes.
Yes.
So he was convinced. No argument.
Okay. So is he convinced like all the way now? Okay, the Earth is a globe, or is it just like just this one little piece?
Okay, remember the God thing?
Yeah.
The Christianity thing? Let's start kicking in.
Okay.
So now it goes from within 6 months, he's an expert on physics, mathematics. His maths just exponentially increased. He's a computer programmer as well, so he doesn't need calculus. He'll write his own formula. I watched him do calculus, and he does his own. He doesn't need a formula. So then he comes back with a vengeance. He's regrouped after 6 months, and he comes back and hits me. And it took me 6 months, or he was on me for about, I only got this a few years back, the orbit of the Earth. And then he started doing things like, he said, basically we both came to the conclusion, how does the Earth travel 1 billion kilometers and come back to the exact same spot without any losses? And he goes, that's what he kept coming at me with. He says, it's a lossless system. I says, oh, yeah, it is too. Okay, how can it do that? Sorry?
It's nearly lossless, right? Science doesn't claim that it's perfectly lossless.
Well, when you're taking the moon is every day the moon transfers, was it 2 with 20 noughts after it, litres of water, pulls on the Earth every day, right? And then the Earth comes back to the same spot.
No,
so if you actually look at those...
Well, that's interesting. I mean, I don't want to interrupt you. But
no, it does. It comes back
the Earth slowly... Sorry, the orbit of the moon causes the Earth's rotation speed to slow down year on year. This is a known, measurable, mainstream science fact.
By how much?
Microseconds per year. I don't know. We could look it up. But the moon is slowly drifting away from the Earth.
Does that make
as the energy, and it's as they're getting into tidal locking slowly, right? So that's causing the Earth's, because right now the the moon is lagging. I could have this completely backwards. Somebody correct me. The moon, I believe, is lagging the 27-day cycle. And so the Earth spins, the Earth spins faster than the moon goes around the Earth. And that causes the tides, and that causes that drag. And there is going to be a loss there, right? And that loss will transfer some energy from the rotation of the Earth to the orbit of the moon, which accelerates the moon and slows the Earth.
Yeah,
and
that's
so
true.
The moon drifts away slowly from the Earth because of that added energy, and the Earth's rotation slows.
True.
So
yes,
so if you dig into this, you'll see that mainstream science says that, like back in dinosaur days, the moon was much larger because it was closer, and our days were shorter. I believe that's correct. So when I say it's not perfectly lossless, right? It's just almost lossless.
Yeah. Well, it's accurate. It comes back to the exact same spot, accurate to 13 decimal places. Okay.
Okay.
If you measure the longest shadow to the longest shadow at the South Pole.
Okay.
So if you look
maybe. I haven't looked at that kind of decimal places. I can't confirm or deny 13 decimal places. That sounds like a lot, but
yeah, it freaked me out too. And it's milliseconds a year, like I say. Now you're measuring
milliseconds a year.
Measuring that with a pendulum clock. So how can you be that accurate? We got measuring things with pendulums. So
they don't measure milliseconds with pendulums, right?
Yeah,
they use an atomic clock.
They measure. Yeah, well, it's a pendulum still. Isn't it?
Okay, you're making the analogy that an atomic clock is still a pendulum because it's got a cycle to it.
Oh, it's an oscillator clock. An oscillator clock. It goes through zero, doesn't it? Zero crossover point.
Yeah.
So at some point,
analogous.
It's not measuring anything. Sure. At some point, it's not measuring anything because it goes through zero. So,
okay. Cool. So back to your journey. I'm sorry for the distraction.
We won't go into clocks because we're really off track now.
Yeah.
You can't measure.
It's amazing. Let's summarize that. It's amazing that the Earth rotating and going around the sun, that the losses should be so very, very low that the stars line back up right where they were the year before, right?
Well, the stars. Remember the longest shadow to the longest shadow? Or the shortest shadow to the shortest shadow. That's a year. Anyway,
yes, that's a solar year. Yeah.
That's a perfect clock. The Earth is a perfect clock. If you want to measure a clock,
perfect.
It's only inaccurate to milliseconds a year. Geez, I'd like to have that clock.
Yeah, that's a darn good clock. Yeah.
And if it's accurate to 13 decimal places a year, heck, I really would like that clock.
Yeah, you bet.
How do you measure a clock? How do you measure a clock that's accurate to 13 decimal places? You can't measure it with a pendulum or an oscillator. I've got to keep thinking oscillator because an oscillator's got a zero crossover point.
Yeah.
Okay. Let's
jump forward in your story.
Okay.
Your friend was into the flat Earth. He didn't believe in rockets. You showed him rockets work.
Right. So then he
got into science. And now where are we at?
Now his science is coming back on me. In 6 months' time, he's kidding me stuff I can't. This thing on the Earth. I'm thinking, oh, whoa.
Okay.
Heliocentric model's got some hiccups in it. So that's when I started listening to him then.
Okay.
And he would come back with another, probably every couple of weeks, he would come back with another thing to make me think. And this is the level of stuff he's coming back at.
Right.
Now, this is you you don't get these discussions on the flat Earth forums.
Not
So,
usually. Usually they're pretty.
Then we went down the normal flat Earth road. You know, we've got to measure
Okay.
the curve of the Earth with the lasers and that sort of stuff.
Right.
So okay.
As I recall, you decided that was pretty inconclusive in the end, right?
Well, yeah, you know, you do the old trick where everyone does it. They get the laser out, or they get the telescope out, and they measure the curve on a lake.
Right.
So we did all that, and we went to the lake a lot. Like I said, went to the lake so many times the police pulled me up.
Like, what's this creepy guy down here with a telescope, right?
Yeah. So but he gave anyway. One day we're measuring this thing, and just so happened I moved the telescope or did something, and I thought, oh dear, telescopic sights, theodolites have all got an inherent problem in them. They've all got this error. So then 2 years later, I had to invent a new type of telescope to measure. So it took me 2 years. I had to patent that.
Yeah, and that's I remember this. I actually wasn't really following your progress through those. And I felt a little bad about it when I did finally see it and then commented. Your what you discovered, as I understand it, is that the casing of the telescope and the optics of the telescope are not necessarily aligned, that nobody bothers with that.
No.
And so you went to great lengths to make sure that yours could be perfectly aligned, right?
That's right. So basically, if you look at a gun is a very good example. With a telescopic sight on a gun, what we do is we look down the barrel and you get a rough idea where the bullet will land.
Yeah.
So you fire a bullet.
Yeah.
And then you say, well, it's on target. Now I'll adjust my telescopic sight crosshairs to hit that point.
That's what we do. Yeah.
That's what you do.
And that I think was essentially my comment was we don't care. we don't care that the telescope and the casing are aligned. What we care is that the optics are aligned with what we want to see or to
what
hit.
You want to hit. You don't care how the bullet hits there as long as it gets to the right spot.
Exactly. Yeah.
Now you need So the first thing everyone does then. So I'm here. So here I'm on this journey with this, making this most accurate gun in the world, right? So you see things starting to, I guess, parallel, come into, I guess, what would you say? Yeah. So then I realised that, I need to learn crash course on ballistics. So what's going on? So first thing you see is all these YouTube shots. People gets up and holds a gun. Well, from his shoulder, someone does a shot and fires some bullets at a target and says, "Oh, this gun's really accurate." And I'm thinking, you're holding that against your shoulder,
right?
Yeah, I've got a jig that doesn't move to 1 micron. And you're holding this against your shoulder and seeing where this bullet lands. I'm thinking, people don't understand ballistics. So then I started on another journey of recreating how to target ballistics. So that's another journey.
Right.
So basically, the sum result was I had a frame of reference that was locked to a physical and the optical were both in a line. So if you want to do measurements, that's another 2 hours talk. So I think we should probably keep
so where are you now? How about that? Where have you landed on the science skepticism spectrum?
Okay, I guess I went from a flat Earth. I didn't go to flat Earth. I went I haven't gone flat Earth yet because I don't think that's not right. But I've broken away from the heliocentric model.
Interesting. Okay.
I've broken away from that. Like I can understand if the planets were powered, that would work. And I did a little video on powering the planets. If they were powered by antimatter, that would work.
Okay.
But they will not work. There's just perpetual motion. Nothing works.
Right.
You take, like I said, the moon extracts so much energy from the Earth.
Mm-hmm.
So if you go to my experiments with the ball bearing rolling down the ramp, you might not have seen them.
I don't think I saw those.
You can't roll a ball bearing over a meter down a ramp and get the same measurement. So how can the Earth go around, travel 1 billion kilometers, end up at exactly the same spot to 13 decimal places? We can't even get a ball bearing to roll down a ramp.
Okay. What about satellite?
Sorry?
Because you mentioned you were involved with NASA earlier in your career. Satellites, man-made satellites orbiting the Earth, are they real? Do those exist?
I
mean, you used to think so, right? You were
satellite dishes.
Satellite dishes, for example. Yeah, sure. Are they not
pointed
at?
I was signing like ground station dishes for TV stations.
Okay.
Pointing at satellites.
Yeah.
Of course they're up there. There's something up there.
Okay. So the satellite definitely orbits the Earth. And those things have a very limited power supply. Right?
Yeah.
So we're cool with that. We get that. But a planet couldn't do that? The moon can't do that?
Well, it does, but it's sucking because when it goes past the Earth, it displaces 2 with 20 noughts liters of water. It pulls that much from the Earth, right? Now that's that's like rolling a ball bearing down a ramp, and it's not like breathing on it anymore. Going, phew. That's like letting it brush a hair on your head.
Right.
Right. So that's putting a little hair on your head.
This brings me to something that I think comes up very, very often in this type of conversation, which is it seems like.
Right? Okay, don't worry about seems like. I've measured it.
Okay, have you calculated how much energy the moon steals from the Earth during an orbit?
Yes.
Okay, and have you compared that against what the heliocentric mainstream science says the value should be?
Yes. Oh, they haven't calculated. No one knows it.
I dispute that. I think we could Google that right now, and you can find it.
True. Yeah, I agree. They, I guess, you got me on that one. I will say
most people just say it seems like it should be a lot.
I haven't seen it, but it's a lot. It's not. It doesn't.
It's a lot, and that's why the moon recedes from us. I mean, the moon is known to recede from us.
Since when it was been observed? So this is this for certain.
Okay.
How do you know that?
Sure. Well, let's check it out. Let's see here. Moon rate of recession. Yeah, let's see if we can let's see here. I gotta wrangle my here, put that over there, and I'll put this up here, and let's turn on screen share. Share. How about we'll share that? Okay, I'm gonna just put moon rate of recession into Google. I don't know if you can read that on your screen. You can do the same thing on your side if you want.
You just tell me the numbers.
Okay, well, the AI overview that Google puts up at the top just says 3.8 centimeters per year, that the moon gets farther away from the Earth. And then here it says the Earth's rotation slows down by 2.4 milliseconds per century as a result.
So does that make sense? Seriously, you're displacing that much energy.
This is exactly my point. It's the seems like that seems wrong. That feels wrong, but that doesn't mean it is wrong.
True.
That's
Yeah, I
just
agree.
intuition. That's us falling for the trap of intuition says that can't be right. We'd run the calculations, it's gonna come out right.
Yeah, I agree. I won't argue that. I won't argue. But roll a ball bearing down a ramp.
Yeah.
And let it stop, and it'll stop, say, a millimeter from the wall every time, or say 10 millimeters from the wall every time. But then let it brush past a hair. Okay.
Mm-hmm.
Where will it stop? You can actually start extrapolating a bit,
right?
Because I'm a doubt how they measure 2 milliseconds every century. Now we've never had a clock, and how are you going to measure it with a pendulum clock? You're measuring an isochronic clock with a pendulum clock.
They would have to measure it with an atomic clock.
Again, the oscillator crosses a zero crossover point.
You've said that a couple of times. I don't understand why that's significant. It's something that oscillates. It's anything that oscillates can be the basis of a timepiece, right?
Right.
The very first ones were probably water clocks. Actually, were probably the oldest ones. They didn't oscillate really. I guess they dropped. They would do it like a water clock, like a sand, like an hourglass made of water. That was probably the oldest one. But then since then, we've used pendulums, springs, pendulums on the end of a spring instead of using gravity. And then we've discovered quartz crystals, right? So now everything is based on quartz crystal. All the consumer stuff is based on quartz crystals, right? They're not moving physically. It's an electronic pulse that's oscillating now. And then an atomic clock is the ultimate evolution of that right now. Right, which is like little cesium atom
crystal, like you say.
Now it's down to like cesium has 2 quantum states, and the states shift at a particular speed, and it's very, very, very consistent. So,
right now, the Earth is purely isochronous. As it turns, it doesn't go past the 0 point. Okay, what? This is heavy stuff.
You need to define 0 point then.
All right, so you understand what isochronous? Well, how that word trouble with it. When you roll a cylinder or a sphere along a path, you get an isochronous curve. That means that it's the same velocity at any point on the curve, just like a pendulum swinging. Okay, this is a bit heavy. I don't expect this today. This is a bit.
Yeah, we're going a little deeper than we probably should.
Yeah. Look, I'll do a video on this for you if you like. It started getting into. I started realizing we were measuring things wrong with time, the way we measure time.
Okay, interesting.
Yeah, and that's where you say the speed of the Earth. Getting ridiculous figures of 2 milliseconds. We didn't even measure things. We didn't even have atomic clocks till the 50s. So
so we didn't.
So when you say you're extrapolating too with your figures, I'm extrapolating. I'm extrapolating, and you are too. Come on, let's be fair.
That's right. That's basically right. Prior to like the 50s, like you said, we did not have these measurements. We didn't have this level of accuracy. When they landed on the moon, they put retroreflectors on the moon, and that allowed us to refine our measurements of the distance to the moon. And so at that point, we started getting more refined numbers there. And then the invention of the atomic clock allowed us to refine time. But all of this is like, yes, they measured it over a period of some time, and then they extrapolate that.
Yeah.
well
So
out.
you accuse me of extrapolating, and not in a nice way, I must say.
Okay.
And I'm accusing you extrapolating in a nice way, right? So we're
Fair
all
enough.
guilty. Don't you worry.
Fair enough. Do you want to talk about the pendulum?
Yeah, let's get into that. How are we going for time? Yep. All right.
Yeah, we've been at
Okay,
it for like 36 minutes.
So then the next evolution comes to is once you've gone through the rockets in space, then you go through the measuring with the lasers on the. Oh, that's right. Then we sort of hit I've got this really good telescope now that measures very accurately the
Got some tea leaves in there.
yeah, something I guess the laser.
Mm-hmm.
Yeah, and I've got that now to a frame of reference where I can get a level. That's another thing we're going to talk about, but that's another week journey. So the next evolution was we sort of stumped. Okay, the lake's not really. After being called up by the police, that sort of took the edge off going to the lake all the time for these measurements. So we having a discussion one day about flat Earth, and his mother was in the room at the time, and she's, "Oh, you two talking flat Earth again?" So she says, "Why don't you make a pendulum?" And we both look at her and go, "What?"
I've said it. I think I've said it before. Yeah. Yep.
She said, we look at her, she said, "What, a pendulum?" She says, "Yes, I was reading my mother's nursing physics book, and in it had a pendulum, a Foucault's pendulum, and he used to measure the Earth was spinning." Oh, that's right. We must have been talking about the Earth spinning or not.
Yeah. Okay. Spinning, flat, space, these are all separate issues, but they're sort of related, right?
Yeah. Well, if it spins, then we can, that was another angle. He said it didn't spin, my friend.
Right. It didn't spin.
So we had another avenue to go down.
Yeah.
So then he starts out with the pendulum. So we do the old pendulum thing, go and buy one straight from the hardware shop and dangle it from the roof. And he's got this new house, and he wouldn't let me drill a hole in the roof to hang the pendulum.
Yeah. Okay. That's going to be the problem is getting a place to do it.
I said, I've gyprocked about 3 houses. I can plaster anything upside down. I'll patch the hole. Let me drill a hole and put a proper hook in it. So he wouldn't let me do that. But to his advantage, I said, "Look, there's a light socket there hanging out. We'll just take a bayonet connection, and I'll hang a bit of, hang our pendulum from the bayonet connection in your light."
That sounds good. Yeah.
Well, I took the bulb out and, broke the end off it. And that wasn't touching anything. It was alive.
Right.
And then we swung it. But that was probably the biggest breakthrough I'd ever came across. Anyway, this thing was swinging, and I had to say, "Look, I can't, this thing appears to be doing the right thing." And he said, "Leave it with me." So I left it with him for a week, and he came back with something that actually was really advanced me, and that's called nodal. Remember I said a nodal bias?
Mm-hmm.
I might have discussed that. Hits the nodal bias, and that is.
Let's summarize it. Yeah, please summarize it for at least for the viewers. What do you mean by nodal bias?
Well, okay, well, let's go back to a little demonstration here. I thought this might help. Remember I said I should have started off with a plumb bob, but I started like everyone else swinging this thing. You got to get the perfect plumb bob. So here's a perfect plumb bob.
Okay.
Perfect, right? Ooh,
if you say so, it's upside down.
Oh, it must have a bias. Look at that. While I'm holding it, it's got a bias.
Right. Right.
Oh, there's a bias.
Uh-huh.
If it had no bias, it would stay there without me holding it. So what we do
Total
with the
tangent. Let me pause you just for total tangent. Shout out. What was the video? Oh, you know what? I'll have to put a link up here later. Somebody just released a video. One of the people I follow that talks about the fact that we all assume what you just said is that if it's perfectly balanced, it should hold forever. And actually, it turns out it's kind of controversial, but mathematicians have shown nope, that's not true. It'll fall, which is really interesting. It's a mathy thing. So I'll put a link up there. But okay, back to what you're saying. I agree with you. It's falling over. Why is it falling over? Because there's something uneven about it, right?
Uneven, yeah. So we haven't got a perfect plumb bob, have we? But using this demonstration, we can actually see that it's not perfect. However, when we stick it from the roof, like
yeah.
Oh, look at that. Oh, look at that. Yeah, it's still perfect. Look at that. It doesn't fall. It doesn't,
Well, I mean, in this demonstration, it's the friction at the mounting point that's causing the angle. But normally with a plumb bob, you're using the gravity vector to align your plumb bob. Right?
Well, there's a really good hey, look at that. It doesn't fall now.
Well, that's because you've got the friction in the mount, right?
Right. So now you see what I'm saying? Friction bias. A slight friction
yes, okay.
bias.
That's the point. The point is any friction in your mount point or the cable holding it is going to bias the result.
Exactly. So it's going to bias in some direction. Theoretically, it should be a chaotic device, and there should be no attractant at all. It should be so random, falls floppy anywhere, almost like this. Falls anywhere, each direction. That would indicate there's no attractant anywhere, so it's purely a chaotic device. Maybe a bit heavy. So then, right.
So let me get a quick review here. Your friend had the pendulum hanging and swinging, and what you found with your very first test was that the pendulum did what? Did it turn like a Foucault pendulum was expected to? Is that what happened, or did it not do that?
Yes, it did.
It did.
Except if you turned it around and faced it another way, it would turn another way. But what happened with the node bias is, no matter where you stick it, launch it, it will actually come to rest at some node. So if you launch it, I guess.
So it wasn't turning in a circle uniformly. It was trying to turn to a particular heading. Is that what you found?
That's right. That's right. And it'll actually hit that node and not jump out of it. So
right. Okay. So it's got some kind of tendency to go in a particular direction. That's not what they're supposed to do. Right?
That's right. Now that can fool a lot of people. They'll think, oh, look at that. It's starting to go anti-clockwise and it's doing it at this rate. Take a look. But if they let it swing long enough, it'll hit that node, that spot that it's traveling towards, and then won't move. It'll stay there. So if you actually could pump it for 33 days, it will never jump out of the node, out of that lock.
Did you have it pumped, or was this just an unpowered pump?
No, unpowered.
Unpowered. So it's not going to swing for 33 days.
No, but he actually, different parts of the room, he detected that. So he actually put a lot of, I was aiming for a perfect pendulum. He was aiming for one that demonstrated this sounded like he was aiming for more exaggerating the bias, right? To show that the bias was what's causing the pendulum to swing.
So for anybody who's just curious about this pendulum thing, but depending on what angle, what heading, compass heading it was launched at, it could be made to go clockwise or counterclockwise just by changing the launch heading.
Yes.
Okay. So clearly not being caused. Absolutely. This rotation is, we can eliminate the rotation of the Earth as the cause of that, right?
Exactly, yes. You have now got a false bias. Now, you remember in 1851, when this was the final experiment, the pendulum, when Foucault launched the 1851 experiment, excuse me, this tea leaves are wrong choice.
Okay.
Probably a large percentage of the population of the Earth, thought the Earth was flat in 1851. There's a lot of people.
Wait, what? Say that again. You're saying researchers thought the Earth was flat?
1851, a lot of the population of the Earth believed the Earth was flat.
Right. We're not really talking about scholars or anything here. We're talking about just folks.
But the general population, just like today. We all know it's a globe. They all say it's a globe. So, but in 1851, there was. So when Foucault launched his pendulum in 1851, it was huge. It was bigger than the moon landing, because what happened was people for the first time they knew they didn't have rockets, they didn't have all this stuff that we got today. They knew the Earth was spinning. Up until then, no one really knew the Earth was spinning. We didn't know where the Earth was spinning or the stars were spinning. Right? So
right. I don't know about until 1851. Yeah, I mean,
So
there was debates.
Well, the pendulum went crazy after that, because you could just do this experiment in your kitchen.
They have one at Griffith Observatory, obviously, quite famous, and I suppose they have them. Do you have any in your area? Any display type?
Don't go down that rabbit hole. Don't go down that rabbit hole.
Well, I would like to hear your thoughts. I mean,
okay.
Let's cut to the chase a little bit. Get a little bit more exciting. What you found in your friend's home, and then now you have reproduced again you've gone to some extremes to try to remove bias.
Exactly, yeah.
And what you have found is your pendulums do not precess. Right? That's where we're at right now.
That last experiment, yes. If you have a look, there was no precession.
Right. So
if I within those.
So there's no precession in yours, and yours are extremely unbiased. What does that say about the one that's at Griffith Observatory that clearly precess? I've seen it. I filmed it. Thousands of people have seen it. Are they faking, or they just have some bias that happens to line up with the calculated results? Where is your head at now?
Okay, let's go back to 1851 where I was.
Okay.
Everyone started making these pendulums. Thousands, hundreds of thousands were made. It went crazy. This is bigger than the moon landing. You've got to go back to the mind. I mean, we didn't know the Earth actually spun. We assumed it spun back in 1851. But now you could get one of these things, hang it from your kitchen and swing it and do your own experiment. So you can imagine thousands of these things were made.
Okay.
So what happened was some would go clockwise, as they should do. Some would go anti-clockwise, as they should do. And some went straight ahead, as they should do. So basically, there was a randomness about these things. No one actually got a defined result. Now, actually, clockworkers were making these things as well. People into precision, and they were getting ambiguities within the results. So there was a lot of ambiguity, and there was a lot of questioning. whether the pendulum was actually showing the spin of the Earth. So
okay. I mean, this is
you're fact checking me here.
No, I was going to respond to somebody. There's a guy
So-
named Mike in the chat that says, "Funny how whatever this bias is makes each pendulum process exactly the amount predicted by the math." Blah 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 blah. And I didn't even. I'll just verbally respond. No, Peter is saying that's not the case. That the pendulums do not exactly predict. They don't all match. Some of them happen to match, but some of them completely did not. That's what Peter is saying now, is even in 1851, some of the pendulums did not have the same bias. They didn't have the same precession rate, even back then. And now Peter's absolutely do not. It looks like your bandwidth has gone pretty bad. Can you hear me okay? Uh-oh, we might be losing Peter at a critical moment here. So I'll vamp for him a little bit. I'm personally not making any judgments at all. I'm just trying to repeat for the audience what Peter has explained, which is that in 1851, Foucault's famous pendulum showed the correct amount, but thousands of people went out and made duplicates, and some of them did not match that predicted value. This indicates, right, that, oh, looks like Peter is back. Are you back? Are you okay? I'm not. He's not. Maybe he's not hearing me.
Yeah, I'm back. You were there all the time.
Okay. Okay. Am I doing a good job of explaining what you're trying to say? Okay. I'm worried that this might be a network problem. Some did not. Big surprise. Okay. What's up with this comment here? Some did not. Big surprise. I think not. Well, personally, I find it surprising. I would have expected that. I mean, like we've always been told, right? We've been told the short version. We always get told in science class, we're always told the short version, which is Foucault pendulum rotates because the Earth is turning. Done. That's it. If some of them don't do that, to me, that indicates probably that my first guess is that means that the signal we're measuring is very small, and that makes this measurement very unreliable. Yeah. Oops. And this is what Clive is saying. It is notorious. I have, in the past, I've seen many people try this, and you can find it on the internet. Lots of people are successful with it, or at least they seem to be successful. But you can also find people who have failed. And Peter has gone to extremes to try to eliminate any bias in this situation by using. Peter, are you able to respond? Okay, he's not responding, so I'll speak for him. One of the first. I hear you. I hear you.
Yeah, I could hear you. I can hear you.
Okay. Do you want to explain some of the things you've done to eliminate bias?
Can you hear me?
Yes, I hear you. We hear you.
Okay. I sort of didn't lose you at all.
Oh, okay.
You got some pretty bad fires there, haven't you?
Yeah, we've had fires on this end, but I'm safe. The internet still works here and stuff. Okay. The
Okay.
the back and forth seems to have lost. Okay. Well, I'll go.
I think this. You're breaking up now. I don't know what to come in here, whether you can hear me or not.
We hear you. Or I hear you.
Okay, you sure? Okay, well, I'll just talk, hoping that you can hear me.
Okay.
Basically, yes, in the 1851 scenario, a lot of pendulums indicated inconsistencies, which threw in doubt the whole concept of the pendulum. So I don't know whether you're getting this or not.
Yes, I'm getting this.
So that's where.
And in modern times, lots of museums have them on display, right? And so, where's your head at with those? What are you thinking?
I missed all that. But I'm assuming you're saying where am I going to now?
Okay, we can do that. That's good.
What really sunk in was the pendulum was supposed to be the final experiment to prove the Earth was spinning.
Okay.
It was supposedly end any debate. But straight after that, scientists started experimenting, like Morsley and all those experiments. So it was to supplement the pendulum, or was there doubt?
Okay.
Did you get any of that?
If you can hear my response, I mean, I don't know whether in history anyone ever referred to this as the final experiment. I don't think anything's going to be a final experiment ever. I think that's not how science should be done, or ever really is done. We are constantly developing new things and retesting old things if we're doing our jobs right. Right? Like, for example, we ask the question, is the Earth spinning? Our first go-to is probably going to be Foucault's pendulum. And your results indicate, no, it doesn't look good, right? Doesn't look good. So I might say, okay, are there other experiments we could do that could either confirm or deny the first experiment? Does anything come to mind? Some folks in the chat are saying mechanical gyroscopes would be the next thing to go to. And then after that, I would say, obviously, after the mechanical gyroscope, and it's like its cousin, the gyro compass. After that, I would ask, what about an optical gyroscope? And then after that, I would probably say, what about weight distributions across the Earth? And then I guess after that, I would ask, what about Eötvös effect and orbital mechanics? How does this all play into this? Thanks, Thunk.
Yeah, I'm missing most of this.
Oh, that is so unfortunate. These are the questions I really wanted to hear your thoughts about. Can you see the chat or if I put a, yeah, let's do a chat. Let me do a private chat at you. What about gyroscopes? I'm going to say mechanical gyroscopes.
Yep.
How about that? Can you see that in the private chat?
What about mechanical gyroscopes?
Right.
Yeah. Well, there's a question. There's a question. There's a question. Why did Foucault jump straight away to the gyroscope? Why did he do that?
If you can hear me,
That was
presumably
intrigued me all the time. He jumped straight
to back up his results to get more precise results. Isn't that
He realized the pendulum
use science?
had a zero crossover point.
Isn't that how you science? Is to multiple avenues of investigation.
Yeah, true. Yep. Yeah, I agree. Yeah. But what made him go down what triggered the gyroscope? Someone else had already invented the gyroscope before him, remember? He wasn't the inventor of the gyroscope.
I don't know.
Wasn't someone else?
I don't know that.
Did it before him?
I don't know that.
The concept?
I would rather ask not what did he do, what should we do?
Really, yes. No.
Did that chat come through?
Yeah.
What should we do? I mean,
do you think this is getting too hard? Yeah. Do you think it's getting too hard for the viewers?
Yeah, it is pretty rough. I'll tell you what I would like to do. I'll say some things. I'll put this in the chat too. This is rough. The internet's is bad. I'll say some stuff. And how about you take 5 minutes? Yeah, I'll tell you what. How about you take 5 minutes to say whatever you would like to. Then I have some stuff for you. You can watch the recording.
Say whatever you would like to say
later. And we can try again.
I think that's okay, but I think we have people who are watching this, and I wouldn't like to be watching a video with disjointed audio and disjointed video.
Okay.
If I was a viewer, I think you'll lose your audience pretty quick.
Yeah, I'll agree with that. So for people who did tune in, and for yourself for later, let me just crash through the stuff that I think that is relevant to your current pendulum stuff. Let me do that really fast, or as fast as I can, I guess. Okay, I'm going to present.
I can restart.
Yeah, give it a try. While you're restarting, I will do this stuff. Cool?
Okay, I can restart.
Try a restart. I'll be here a minute.
Okay.
Okay, hold on. Okay. Hold on a sec. Okay, hopefully Peter is going to restart. And I wanted to share this. Okay, I just wanted to share this real quick. If Peter later on maybe can watch the video, if we don't get to reconnect, he can look at this and give me some of the numbers that I'm talking about here. This is my diagram of a pendulum. So here's the mounting point of the pendulum, and it swings down here. So I would like to know what is the length of his pendulum, and the way he tends to measure it, I think, is the displacement across the bottom. And then he's got a laser that he's shooting across the pendulum here. What is the height? And I've measured it from the mounting point down to the laser. And I want that because I want to try to see if we can even extract the angle that his pendulum is at. This is really a core problem with Peter's setup is even getting that. Okay, hold on. Let's move this over there. Okay, so if we draw this, I have drawn this now from a top-down perspective, and I'm showing that he's got a laser that's sweeping a beam across. So this is the pendulum swinging this way, swingy, 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 swingy. And as the pendulum rotates, right, as it turns from a top-down perspective, I've shown it turn. So now it's not swinging. This is the original launch direction. And after time, it changes to some angle as it rotates this way. And what Peter shows in his videos is this laser hitting the back wall. And as the pendulum swings, the string that it's hanging from blocks the laser, and you get a little shadow on the back wall. And so we see the shadow on the back wall going back and forth as the pendulum is swinging at an angle with respect to the laser beam. And so I did some math, and I just do some math. And what I'm trying to do is extract what is this angle, the angle that the beam has precessed to based on those shadows on the wall. And this is, so I just made up some numbers. Let's see here. Where is that? Yeah, this is it. So I just made up some numbers. Imagine that the pendulum is 4 meters long, and it's, the laser is at 2 meters off the ceiling or whatever. I just made up some numbers. And then based on the angle that it has precessed to, I can predict the difference in millimeters on the shadow on the back wall. And what I'm finding with my guesstimated numbers is that this isn't going to work. I'm getting a maximum of like 0.1 millimeter of difference. And so I think we're going to need a better angle measurement technique. So that's what I'm going to probably try to brainstorm. What I would say is, hey, let's brainstorm. Let's get the community to brainstorm. What's a better way to show the angle of the pendulum so that what I would like is just a graph. I would like to graph angle of pendulum versus time. And I would like to see, is that a straight line? Is it a curve of some kind? What exactly is that pendulum doing? And then we can ask all kinds of questions like, does it vary based on something, right? What does it vary based on? Does the original release direction affect something? Is there a bias? Like Peter was saying, there's a bias in the room. There's a particular angle it wants to be at. What is that angle? Identify that. Are there any variables that we can look at? Okay. And then the other stuff that I think is absolutely worth talking about is imagine that Peter's right and the Foucault pendulums do not work. What does that mean? What does it mean about the Foucault pendulums that we've all gone and seen in the world? Like the one at the Griffith Observatory here by me. I've seen it. I filmed it. It definitely works. I feel like it's legit. So if it can't be legit, is it just a happenstance that pendulum just happens to match the prediction? Right. And so that would be a question I want to know, because if we're asserting that pendulums do not precess, then all the people who are showing us pendulums that do precess, are we saying that those people are untrustworthy? That's an immediate question that we should look at. And then I think it would be worthwhile to say, well, okay, what about the other findings, such as just a high precision mechanical gyroscope does show the rotation. An optical gyroscope. We've all seen Bob Nodell's famous optical gyroscope measurements that it does show rotation. If you're not aware of critical think, several people have done this, but critical think has taken it to the extreme, where he has measured the weight of a reference mass at different places on the Earth, and he'll show you a graph of how the weight varies with latitude. And we think that's because of the rotation of the Earth, right? And in orbital mechanics, we launch our rockets to the east. Not always, but we prefer to launch our rockets eastbound. The reason for that is because we're taking the rotation of the Earth. The speed of the rotation of the Earth is added to your velocity if you launch eastbound, and just save fuel, right? And that's a measurable thing. Yeah, Etvoss effect. Wolfe did this. He put a weight on a scale, and then he flew eastbound and he flew westbound, and he showed, there's a lot of turbulence, so it's jumping around. But if you average them out, you see that the weight weighs more going one direction and less going the other direction. Here comes Peter. Peter's coming back. So these are all things that we want to look at and see, what does it all mean, right? What does it all mean? Peter, I'm adding you to the stage. Hey, can you hear me? And can you speak?
Sure.
Okay. I think, alas, I think that's probably going to have to be the end of our live stream. Doesn't seem like the interwebs is going to work out for Australian folks. Is there anybody in the chat who wants to add something to the conversation that maybe Peter can read later? If so, I'll give you guys a few minutes to do that. I will repeat that for Peter's a very practical experimenter. and he's done great work. So, people sometimes want to get on here and make nasty comments. No, he's just very practical. He's made a very nice pendulum. The only thing I would say that's is wrong with Peter's pendulum is it's not tall enough. Conventional wisdom says that you need a very tall, a very long pendulum to reproduce this effect. And I don't think Peter's is maybe big enough to do it. Other than that, so that's what I would want to do, and I would even offer to do is try to find locations that allow us to hang a taller pendulum. How tall, if you can hear me, how tall is your pendulum? Okay, seems like he's not getting that. Other things that have come up are when you burn the little
sort of. I'm guessing you're asking how tall.
Yeah. Yeah. Okay. Yeah, we're not getting you at all, or at least I'm not. Okay, so let me throw some stuff at you.
What should the pendulum be?
How tall should the pendulum be? Wikipedia said,
the taller the better. Will give you a longer swing.
Foucault pendulum. Yeah, taller the better. How tall is yours? Do you know? I mean, you must know. 12 meters is what Wikipedia says. 12 meters is what Wikipedia says is a ideal minimum. So yeah, I would say we should look for a place that's very, very, very tall, and try to do one taller. See, how does that do it? What I think, really what I'm trying to say is that Peter is going to do some great experiments, and I'd like to see him keep on doing experiments and try lots and lots of different things. Try to get to the bottom of as many different things as you can. Because we have supporting evidence of other kinds besides just the pendulum, I find it very unlikely that your pendulum is telling us the Earth is not rotating, because we have mechanical gyroscopes, optical gyroscopes, gyro compasses, weight measurements that are all in line. Everything's all falling into perfect line. It's hard to imagine that they're all wrong in the same way, and that your Foucault pendulum is showing that. And maybe there's something else that we haven't found, and I think it would be fantastic to keep looking. Ultimately, I think that's my message. If there is a message, is I will keep my mind open to all possibilities, and I think we probably all should. Personally, I think this preponderance of evidence, since we have so many different lines of evidence, is very strong, and I'm hesitant to be swayed by one person's pendulum one way or the other, right? It would take more than that, I think. But that doesn't mean my mind is closed to the possibility. And I'd like to have, I would ask anybody from the opposing side to have the same, at least, openness that maybe the Earth is not rotating, but we have all this other data. Maybe there's something that's worth looking at. Okay. Unfortunately, that's the end of the interwebs for us today. Yeah, here is Blue Marble Science saying, I think Peter's pendulum is just too short. I haven't done the numbers on this. I know that Flat Earth Math spent some effort doing the math on this and to try to construct one. And his assessment was that it had to be very long in order to be good. The Griffith Park one is apparently 40 feet long. Yeah, I'll go along with that. It's probably right. Okay, and so, yeah, and if somebody can go deeper, if somebody's able to go deeper with us and tell us exactly why they have to be so long, and why we're getting results like Peter is getting. If you have a speculation of something to contribute in a positive way to what Peter is trying to do with his experiments, like what is worth looking at, what else is worth trying. My initial thought is, my first thought, Peter, if you're watching this, is can we get a better reading of what angle the thing is at while it's swinging? Because the marks on the back wall aren't working. How could we get I want a graph, like make a graph of the current angle over time. So ways to get the angle would be a brainstorm. We should maybe brainstorm how do we get better angles. And then after that, I would say, what if we can we get a taller one? Because all these people are saying it has to be really, really tall. Can we get a tall one? Is there somebody we could, team up with to get us an indoor space with no wind where they'd let us hang a pendulum for days and do a thing? Okay. Here's somebody, S. Thurston 2, suggests something we might look into. Somebody showed one with a short pendulum. I haven't looked at that. Maybe that's worth looking at if they have some trick that we haven't considered. Okay. I think we're going to have to call it there. Peter, if you can hear me, give us a response. Okay. Yeah. Hotel in Phoenix, close lobby. Yeah, I think that's where we'll have to call it. Unfortunately, the internet isn't working with us today. It was great talking to you. Great hearing your story. And maybe we can try again. Hopefully you're going to keep at this, and maybe some folks here are going to watch once in a while and see as your results come out. All right. Okay, y'all. Have a great one out there. Stay safe. Be nice. Be open-minded. And I'll talk to you next time. Bye.